morning today, everyone, and in this video I'm going to be talking you through how to create a virtual library of compounds. These are all commercially available compounds from companies like Enamine and Wuxi and MQL, and they focus on make-on-demand compounds from the catalogs from these companies, and we're going to be using those in combination with a fragment of a molecule to create an even larger molecule. So we're essentially doing fragment growing or core expansion, and we're going to be using the chemicals in this database as building blocks to open up a lot more chemical space for virtual screening, which is obviously a key part of early phase drug discovery. And so Zinc 22 currently has about 55 billion molecules in 2D and about 6 billion in 3D. So if we go into the first database, so this is the 2D database, you can see the libraries. So there's about 96 billion molecules in total in this library, and that includes molecules with all the way from 4 heavy atoms to 49 heavy atoms, so very small shard or fragment-like molecules, all the way up to big macromolecules. Okay, and they're divided by heavy atom count along the top and log p value along the y-axis, and you can select different sub-libraries. So here I've selected the fragment libraries, and you can see that even within the fragment sub-library there's 70 million small molecules in that set, going from 8 heavy atoms to 16 heavy atoms and down to log p of 2.4 and -2. So yeah, this is obviously a large data set, and for our purposes maybe some of those are a bit too big, so we're going to go for the shards data set, which is a bit smaller but will suit us a bit better for the task we want to do at the moment. So that's 5 to 10 heavy atoms, but that still includes 177,000 molecules in that data set. And so what we're going to be doing now is downloading this data set, and we're going to be using the we-get method, and that is done by going to the top right. And if we click on that menu, it will show us all of our tranches. So these are the sub-libraries and the names in terms of their heavy atom count and a log p value. And we're going to download the purchasing information format because that gives us the smiles and the zinc ID codes, so we can trace them. And the method we're going to use to download them is wget, or the wget. And wget is just a computer program that retrieves content from web servers. Okay, so this is going to give us a link that we can then follow. So I've downloaded the wget file, and this provides a link to the zip file. So if we go into the Colab notebook here, and for those that haven't used Colab before, it's very easy to use. It's essentially a series of cells that run a Python script or R script. You can use Java, and yeah, you don't need to know how to code to use this notebook. You essentially just need to upload your files and press play on the cells, and once you've uploaded your wget file to the files in your Colab, or you've dragged it and dropped it in, then you can run the then you're going to start to see the files downloading into your Google Colab drive, and they're going to be organized by heavy atom subfolders. So each of those subfolders will be subdivided by heavy atom and log p. And then we're going to extract those zip files. So we're going to decompress them. And this is just an example of a script. So this is going on in the background. You can hide it or you can show it. But this is just unzipping those directories in there containing the smiles. And then what we're going to do is count how many smiles are in all of the libraries. So we can see that there's just under 3 million smiles in that library in all of the directories that we've downloaded. And now what we're going to do is we're going to display a sample of each of those libraries or each of those subsets as a data frame, so we can just get an idea of the format. And that will contain the smiles and the zinc ID, so essentially just the molecule itself, and then a descriptor of its identity, so that we could trace it back later on if we wanted to buy uh, these molecules. Okay. Now, a lot of the molecules in there are probably going to be duplicates. There's probably going to be repeats of smiles. So I've taken an example of this from one of the data frames, just to give you an example of what I mean. And to save a lot of computing time and power and expense, we are going to clean up this data set. And we're going to use multi-processing, so essentially use multiple workers or CPU cores to go through these data sets in parallel, just to speed things up a bit. And so these cells just set up a multiprocessor. You don't need to worry about understanding what these do. You can just run them and it will set up a multiprocessor, and it will analyze those data sets, and it will count the number of duplicate smiles inside all of them. And then once it's done that, it will take all of the unique smiles, it will count all of those, and then it will combine all of those from all of the different data sets and compress them into a zip file. You can see that it's running those here, so you can see the progress bars are just telling us how fast it's scanning, and this should take a few seconds, maybe a few minutes. But yeah, I ran this for this database and it took about 5 minutes to run 170,000 molecules. Okay, so really not long. And this is just finishing up here. Here we go, and then it's zipping all of those, it's compressing them into a gzip file. And then what we can do in the next bit is the 2.3 million is the total, and the number of duplicates removed is 2.1 million. So that makes sense, because that leaves us with 171,000 unique smiles, and the original database said there was about 177,000. So obviously we've removed 2.1 million duplicates, which is obviously a very large amount that would have been wasted computational power, essentially. So we've got 171,000 unique smiles, and now we can decompress the zip file and view it as a data frame and just look at a sample of molecules here. You can see that we've got the smile strings on the left and then zinc ID on the right, which is good because that allows us to trace back the molecule for purchasing. Excuse me. And you'll notice that there are some kind of odd smiles in there. I'll show you what I mean. So we can display a grid of molecules, and you can see we've got some kind of like boronate clusters in there, which synthetically are not going to be useful for us. We're not going to be able to use those to react with our core or our fragment. But there are some interesting molecules in here. So there's some bromoalkenes, we've got a lot of chiral molecules, we've got some cyclopropanes, we've got some alkynes, oxides, ketals, lots of kind of chemical variety. This is just a small sample. This is only 5,000 molecules, but you can already see we've got quite a variety of molecules in there, and that will only grow when we use the entire data set. Okay, so now we're going to go into actually making the combinatorial library, or doing our fragment growing or core decoration, or whatever it is we want to do. So section 3, creating new chemical space, is where we're actually going to be doing our core decoration or fragment growing, whatever it is you want to call it. And what you can do is you can, if you have a list of smiles, so say you have smiles of fragments, or you have a smiles of a particular molecule that you're interested in, then you can copy and paste it into this text box, and then just press generate grid, and then that will generate a grid of those molecules. So here, for example, we have some molecules of interest. So these are some molecules that are real molecules that are of interest in creating antiviral drugs for coronaviruses. So these molecules showed some activity. fairly weak binding. Obviously, they're quite small, but fairly weak binding, but are worth pursuing because there's clearly some structural activity relationship going on where they've all got similar kind of motifs and are all showing some sort of binding. So we've basically got this kind of pyridine core with a phenyl ring. Sometimes it's functionalized, sometimes it's not, and that's alpha to either a alkyl hydroxyl group, a hydroxyl, a carboxylic acid, or an ester, some sort of hydrogen bond donor. And yeah, so that's interesting. And what we want to do is maybe see if we can grow these fragments out a little bit to um, make them a bit more active, a bit stronger binding. And one spot that you could do this on would be, say, the alcohol. You could functionalize the alcohol, but in this instance, we're actually going to functionalize the nitrogen. So let's draw that common core that's in all of those molecules. So you can see we've got a prolidine here in all of these molecules, and I'm actually going to go for this first one. So I'm going to have a prolidine. It's got two chiral centers. So we're going to draw the stereochemistry for those two chiral centers here. And we're going to draw in our phenyl ring and functionalize that with the fluorine atom. That will help with solubility. And add on the hydroxyl group as well. And then for the nitrogen, we're just going to leave that as an NH because that is essentially our building block. That's our core that we want to decorate. And like I said, you could decorate out from the hydroxyl group, but obviously amines are very good reagents because they can do lots of different reactions. And if we could buy this as a building block commercially, or even just make a lot of it in the lab, then you could use this and you can make a lot of analogues very quickly. So if you press save 2D structure as smiles, it will take the molecule that you've just drawn and it will immediately convert it into a smile string. Okay, like so. And what we can actually do is we can copy that smile string and we can paste it into this smiles to PNG. And run the cell first. Always run the cell first. And that will essentially activate it to run, paste in your smiles, generate PNG, and it will show you an image of your molecule. It's the same molecule, it's just flipped the other way around. The stereochemistry is the same. It's labeled each of the atoms with an indices, so you can see their number, and it's also assigned stereochemistry, and it also allows you to label which atom you're selecting as your vector. So if I select oxygen and then generate the PNG again, it will highlight that atom in red. And obviously we're going for the nitrogen here. That's more interesting at the moment. So we're going to select nitrogen, atom 4, and that is our reactive atom. Okay, and that's good if you want to just save that as a picture and put it into a report or something like that. Then what we're going to do now is we're going to run this cell, which basically it will scan through the cleaned parallel smile gzip file, and it will look for all the smiles in that folder or that file, and it will scan it for functional groups, and it will be defined by a list of functional groups that we have written into the script. So if you look into the script for this cell, then you can see that we have a bunch of different functional groups. You have aldehydes, you have alcohols, alkenes, alkynes, halides, ketones, heterocycles, phosphates, sulfonamides. Essentially, you can add to this list. This is just a list of kind of basic functional groups that you'd expect to see, but you could add even more to this as long as you have the smarts strings for them, which you can generate or you can find online easily enough. We're running the cell now, and it is scanning through those. It's scanning about 5,000 molecules per second, so this will obviously only take a few seconds to complete. And the purpose of doing this is to essentially know what kind of chemistry we can do. So obviously we've selected our amine, but say we hadn't selected our amine, say we had a different molecule and we were thinking, I want to know what reactions I could do here. And in order to know what reactions you could do, with your fragment, then you would want to know what functional groups are present in your potential reagents or building blocks. Okay, so now that's finished and we've generated a bar graph here, and you can see we've got predominantly alkanes, 160,000 of those thereabouts, which isn't surprising because that's essentially just counting any molecule that has one sp3 carbon. You can see there's a lot of alcohols. There's about 45,000 alcohols, which is interesting because then we could use those for, say, Mitsunobu reactions. So you could do an SN2 displacement with the amine, kick off the alcohol, and then you've got a new molecule. We've got lots of alkenes. We've got a few carboxylic acids, not too many, which is a little bit disappointing. So obviously we could form a lot of amides, but you could also download a carboxylic acid library specifically. So you could go into the amine website and you could download their carboxylic acid library if you wanted to explore that further. Lots of ketones. So you could form imines. Okay, and now what we're going to do is we're going to paste our smiles in from earlier into this combinatorial library enumerator, and then copy the path to your gzip file, the cleaned one, and that is going to react those together based off of a list of possible reactions. And you can apply filters here. So obviously in medchem you want certain properties in your molecule, so ideally you want a certain molecular weight, about 150 to, I've put 650 here. Solubility, so log P here is -1 to +4.3, and yeah, it will take a little bit longer if you do pre-select the properties. You could also filter the properties afterwards, after you've run this, but because I have time, I'm just going to pre-filter them so that all the molecules that are generated have these properties. So C log P is obviously solubility, MW is molecular weight, HBD is hydrogen bond donors, hydrogen bond acceptors, TPSA is topological polar surface area, RB is rotatable bonds, and FSP3 is the fraction of sp3 carbons that are present, 0 being none, 1 being all, and that's obviously important for sort of ligand flexibility and degrees of freedom, and maybe you want to set that a bit lower if you want a bit more of a rigid molecule. If you have quite a predefined binding pocket, then maybe that's a good it's good to set that a bit lower so that you're just dealing with rigid molecules. And then SA is the synthetic accessibility. This was defined in a paper a while ago, and I'll try and find the links to that paper, but it's kind of relative. So synthetic accessibility is a rough estimate of how hard that molecule would be to make in the lab. And ideally, because these are all one-step reactions, the answer should be not very hard for any of them. So you could set this higher, because these are all based off of known one-step reactions. But obviously, if your fragment is a bit more complicated, or you've got some interesting building blocks, then maybe you would want to set it a bit lower, so that, or maybe set it a bit higher, sorry, so that you're not cutting those molecules off too early. Right. Okay. So once you have selected your filters and you're ready to run it, you just press the run enumerator, and you'll see that it will start generating molecules, and it will describe to you what filters you've applied, and it will start running a reaction between this nitrogen on your molecule and the different molecules based on their functional groups. Okay, and then it will put those into different file formats. So you'll get a CSV file which will contain the smiles, it will contain the zinc ID and information about the molecules, so log D, molecular weight, etc, etc. You'll also get an output of a text file which will be the correct format for a virtual screen. So the molecules will be named by the zinc ID, and then you'll have a comma, and then you'll have the smiles, and that is a perfectly acceptable format to use for virtual screening just straight off the bat, as is in the next step. So that's really useful. So I've just skipped ahead here, so you can see that's taken about 25 minutes to generate all of our molecules. So that should be loading through just about any second now. And so if we just have a look at the report here, so enumeration summary, it's processed 171,140 building blocks, which is good. And building blocks with no written products, 147,000. So it's a large number, and we'll probably want to do some analysis as to why that is. We can have a look through the molecules that didn't react later and figure out what's going on there, and then we can maybe amend our script, or maybe it's just a case that all those molecules don't contain any of the functional groups that we specified. And then either you could expand that, or you can expand the range of functional groups, or it's just a case that there are no reactive functional groups that could react to an amine in there. Okay, but for now, we've got about 25,000 potential molecules to work with, which is not too bad for a first try. So if you go look in the report here, it tells you the reaction type and the reaction name, so Mitsunobu. It tells you how many building block partner matches there were, building blocks that produced outputs, and then how many of those were unique products. So for the Mitsunobu reaction, there was a lot of alcohols in there, 17,400 products. And then for some other ones, so you scroll down to the Sofex sulfonamide, there's obviously only 165 products in there, so there's obviously not too many. There's only 220 sulfonamides in there. Okay, and then Chan-Lang coupling, 133. But yeah, this is just a little report to show how the molecules were generated. You could save this if you wanted to. Put it into a CSV. If you want to report this, it's got little reaction schemes of the type of reactions that were performed, just so you can inspect them and see, okay, is it reacting like I would expect it to react? And then it's got a bar chart of the unique products by reaction name. So there are lots of Mitsunobu products in there. There's some bookboard Hartwig products in there, so about 5,000 of those. There's a few thousand amides, there's a few reductive amination products for ketones. So yeah, and if you scroll a little bit further down, you'll see previews of the products that we're looking at. So if you go into the bookboard Hartwig one, you can see there's a range of products in there that are from halide displacements, and it's also got the zinc ID and the smile string. So obviously that means that you can trace the reagents back. So if you want to make these molecules, you can just look up the zinc ID and it will show you the reagent that was used to form that product. But you can see just from looking at the bookboard Hartwig library here that we've got some pretty interesting chemical diversity. So lots of different heterocycles with different functional groups coming off the sides. Sometimes these 2D grids get a bit compressed, like you can see here, just because it's a bit crowded and it's the machine trying to save memory essentially. But this is just to give you an idea of the kind of diversity of chemical space that we've just created by just functionalizing that amine. So we've got lots of chiral groups. So if we go and look at the products, then you can see we've obviously got some interesting functional groups in there, including some chiral ones. We've got cyclopropanes, we've got nitriles, we've got cyclobutanes, lactams, we have sulfonamides, we have sulfones, a very large number of molecules with a lot of chemical diversity in there. So that's great for virtual screening, because that means that we're much more likely to pick up some more interesting interactions in those molecules. And yeah, so that's basically everything about this cell. And then if you want to, you can generate histograms to give you an idea of the kind of properties We're going to go through another video how to do this and how to cluster molecules as well, which is obviously very useful for looking at um, how many similar molecules you have in your library. But for example, you can just take a sample of your molecules and you can generate a histogram, and that essentially just shows you the majority of our molecules are in the kind of 300 to 350 range in terms of molecular weight. And you could do the same thing for other properties. So you could do the same thing for hydrogen bond donors and see what kind of distribution of molecules you have with a certain number of hydrogen bond donors. Okay, and yeah, so when you run this script, your zip file will be automatically generated, and you'll get all these molecules written out into CSV format and a text format, which again will be ideal for virtual screening because we're going to be using that later on in another video. And then if you go into the CSV file, you can open up in Excel, or you can even open up just in Colab, and you'll see that you have the smiles, the INC key, the zinc ID, and then other information, reaction type, so where it originated from, molecular weight, log P, all your properties for the molecule as well. So this is great. So if you end up buying these molecules or trying to create a list of molecules that you want to buy, you could run virtual screening, get docking scores, and then also look at their properties and say, okay, well that has that obeys the rule of five, and so that means potentially that those are better than those molecules that don't and have slightly lower scores. So it just gives more credence to your argument for why you would make or purchase certain molecules versus other ones. Okay, so that is basically everything for this notebook, and I hope you found it useful. And please feel free to use it and try and generate your own molecules and see what ideas you can come up with. And then in a subsequent video, we're going to run a virtual screen of these and see how they bind to our target protein.